Thanks for the introduction, and thanks for this opportunity to present in this webinar series. And this is my contact information, my cell phone number, and email address. Feel free to contact me if you have any question after the presentation or down the road. Okay, let's start with a very basic function of phosphorus and potassium and how the deficiency looks like. So phosphorus basically is a energy element. Is involved in the energy transformation and metabolism like ATP. Also, phosphorus is involved with several structural components. It promotes root growth and development and help in seed formation and maturation. So one of the things I like to highlight here about phosphorus deficiency, how it looks like. If you see on the corn leaf, the deficiency start like on the A is purple discoloration. But on the soybean part, you don't see a purple deficiency symptom in soybean because under phosphorus deficient condition, corn accumulates anthocyanin pigment that causes that purple discoloration. But for soybean, that maybe that anthocyanin pigment accumulation is very minimum. That's why you don't see that like a purple discoloration. The only thing soybean does under deficient condition is the height difference. But the bad news for the producer is there wouldn't be a control plot versus fertilized plot in the producer field to identify the height difference. So the potassium, on the other hand, produce really yellowing, like irregular yellowing symptom on the around the leaf edge. It can be on the bottom leaf as well as on the top leaf, depends on the severity of the deficiency as well the growth stage. So the potassium is not a part of any molecular structure, but is involved with the osmotic regulation, like water balance, target pressure, that also controls the stomata. Also, it helps uptake other nutrient, and also is a very under sufficient potassium or deficient potassium condition, plant attacked by different pests and pathogens. So let's talk about that, how crop responds to long-term fertility, of the different fertility, phosphorus, potassium, sulfur, nitrogen. This study conducted or established in Auburn University like 1911. So this age of the study is almost 113 years. So last 10 years yield data shows that for corn, soybean, and cotton, when you have a balanced fertilization, corn yield 130 bushels per acre, soybean 40 bushels, cotton is like 1,300 pounds per acre. But look at the phosphorus and potassium on the red color. The potassium, the one has showing the most yield-limiting nutrient for all three crops, even the more than the nitrogen under severe deficient condition. So everybody would agree that nitrogen would be the yield limiting nutrient in the crop production, but it can be potassium, depends on the how severe you are in your soil. So this soil test potassium value in this study is false less than 15 ppm. Okay, let's look at the why it is the reason. Let's look at some pictures. I'm sorry I don't have the pictures of soybean from their trial, but I do have for corn. So this picture shows the first one is a no lime, the second one is no nitrogen, third one is no potassium, and the fourth one is no phosphorus. And you see that after lime, when the pH was 4.5, nothing is growing. And again, when the soil test potassium was 15 ppm or less than 15 ppm, you see at the very earlier stage, the leaf turn into yellow color. So what does it mean when it's turned into yellow color? Is basically disrupt the osmotic balance and the chlorophyll content as well. So plant is not producing food through photosynthesis because the stomata is closed. That's why it's hurting too badly under the severe potassium deficiency condition. Nitrogen is still at the earlier stage, is pale green, is going to turn into yellow, but it takes a little longer time. So we did a study for soybean and corn under severe deficient condition in potassium, like the salt-test potassium value was 27 ppm around that zone. And it's in the LSU Ag Center Macon Research Station. And we have 5 different potassium rate. And you see the yield is increasing exponentially as you increase your potassium fertility rate. The same site we put the corn trial in 2022 actually, and see under again the zero rate produce only 22 bushels, while we have all 200 unit of nitrogen, 80 unit of phosphorus in that trial, but only thing was missing is the potassium. And see how it increasing the yield with the increment of potassium fertility. So potassium, again, that I said, the stock quality under severe potassium deficiency condition is so poor that plant even cannot stand. With a little bit wind, is fall apart. So let's look at our, so potassium we talked about is very important. Let's look at our current phosphorus and potassium recommendations for soybean in Louisiana. The first table on your left is showing the phosphorus recommendation and different soil test level and soil test value and the recommendation. And it's very straightforward. We have 5 different categories of soil testing, and that we have a corresponding value. But look at the potassium table. It's very complicated in a sense. The potassium, if you look at the medium concentration, it means the critical concentration. It actually changed with the soil type or soil texture. Like we have 5 different soil textural groups. Also, whether the soil is alluvial or upland. So if you think all these, we have basically 10 different critical concentration in Louisiana. So that draws my attention when I started this position 4 years ago. Then we looked at through the past, we had a survey that we brought all the all the information about soil testing and recommendation from different states, and we see only 6 states has this type of recommendation that varies with either CEC or soil texture, and none other than the 6. Everybody is kind of has a one critical concentration for all the soil types. So that I said, based on this information, that draws our attention to reevaluate our soil test-based phosphorus and potassium recommendations in Louisiana. And we conducted like 4 years study from 2020 to 2023 across 61 different locations. And you see all this yellow color is showing the along the Mississippi Delta, that every parishes or county we use, we have 6 different research station trial, and also 12 on-farm research trial actually from the producer field. And we have 39 silty loam, anywhere from sandy to silty loam soils, and 22 clay soils. And we have 5 different rate of phosphorus and potassium from anywhere from 0, 40, 80, 120, 160 pound, either P2O5 or K2O per acre. So we sample this study from 0 to 4 inch, 0 to 6 inch, 0 to 8, and 0 to 12 inch depth. And I will explain why we did that in a minute. So we had around like 2,600 experimental plots to visit and get the yield and tissue samples. So this graph shows the soybean response to potassium fertilization at different soil test potassium values. So the first one is under very low soil test potassium value, where the potassium concentration was less than 60 ppm, that equivalents to 120 pounds per acre. And we have total 10 trials. So on the y-axis, we have soybean relative yield, and x-axis is the fertilizer K rate. So if you increase the fertilizer K rate, the yield actually increasing exponentially until it hits 120, then there is no more increment from 120 to 160 pounds potassium. The second category, where the soil test value from 61 to 90, we have 12 trial total, and the yield is still increasing like almost linearly as you increase the potassium fertility rate. From medium soil test value from 91 to 30, you see there is really very small increment at the beginning with a 40 to 80 unit, even no difference between 40 to 80 unit. So very little increment. But when you see under optimum soil test value more than 130 ppm, you see this is a flat line, and even the line is declining with a higher potassium rate. And we have observed that with a higher potassium rate, you are kind of sometimes you hard yield when you have really droughty condition, you don't have a rainfall, and you create a salty soil condition around the root system, and it's hurts yield. But there is no literature that shows that potassium hurts yield, and probably the statistically is the same. But I'm just talking under severe droughty situation, and if you put really high rate of potassium on that soil and the soil test value is still high, that can happen. So we took all this zero rate, like unfertilized K rate, and make a regression curve with a soil test value. And this soil test value represents 0 to 6 inch depth. So again, I will explain a little bit this graph. You can see similar of this type of graph for like throughout the presentation. So I'm explaining one. So on the y-axis, you have a soybean relative yield. And the way we calculated relative yield, we actually published a paper through FAST that it is unfertilized K yield compared to maximum yield of the fertilizer treatment. For example, if the 120 rate produce the maximum yield, so you are taking the zero unfertilized control yield divided by your maximum yield and multiply by 100, make it a percentage. So the blue dot represents the responsive site at 10% probability level, and green dot represents responsive site at 25% probability level, and all the red dots represent unresponsive site where we put fertilizer and did not see any yield increment. So this is actually very strong correlation that you could ask for for potassium, very clear cut. And we set the critical concentration in a way, again, I'm very strong follower of FAST that recommends the critical concentration is about a 95% confidence limit of the 95% of maximum yield. So the 95% maximum yield, actually, the maximum yield was 97% in this graph. So 95% of maximum yield will be 92%. Then like a 95% confidence interval that falls anyhow, the critical concentration falls 102 to 130 ppm. So on the left side of the critical concentration, you have a deficient site where you expect yield response if you fertilize. And we see a clear yield response, like this model is 100% accurate. We have every site on the left side that responded positively to fertilization. On the right side, we have a sufficient site. And then again, it's expected there would be no yield response. And we found there is no yield response except one trial in the producer field where the soil test potassium value was 300 ppm. But again, without fertilization, it's still producing 94% yield. The data was so tight in the producer field with such a small increment with the fertilization make it significant. So now go back to our original question, like the Louisiana soil test critical concentration varies with different soil texture. And we tested that. This first graph is showing all the silty soils, like anywhere from sandy loam to silty loam soils. We have 39 trials, and we see still that relationship is holding. And the bottom graph is all the clay soils we have, and see the value is anywhere over 100 ppm, and we see there is no yield increment if the value is over 100, 130 ppm. So let's look at the recommendation. So this critical concentration that we have currently is really doesn't vary with soil texture or alluvial versus upland soils. So based on that, and again, that's I said why we did analyze or make a regression for different soil depth. So this is the depth graph that we have soil sampling depth from 0 to 4 inch, 0 to 6 inch, 0 to 8 inch, 0 to 12 inch, and that's the MELAC3 soil potassium concentration. So that the soil test value actually increasing if you taking a shallower sample like 0 to 4 inch. But after that, the value actually statistically same. So there is a stratification, but the stratification is really very minimum. You see the same amount of potassium present down to the soil profile with a 0 to 12 inch depth. That also suggests potassium is leaching down. It's not really stratified on the topsoil. So we made a different correlation with a 0 to 6 inch versus 0 to 4 inch depth and how it falls. And we found really strong correlation with a 0 to 6 inch versus any other depth. And the correlation strength is like 0.99, almost perfect correlation. So the reason for doing that with a different depth, because when I was in Virginia Tech, we conducted the similar trial with a coastal plain soil where the potassium is leached down significantly. And this is the publications where you see on the topsoil 0 to 6 inch, the potassium concentration was 79. Then the 6 to 12 inch was 89, 12 to 18, 133 ppm, and 16 or 18 to 24, 164. It means potassium is leaching down significantly. So that's why we try to develop a correlation with a different soil depth to make sure we account for all the potassium present in the soil, especially around the root zone or rooting depth. And we found 0 to 12 inch had a better correlation and also is reducing almost 30% potassium rate. So we tried same in Louisiana, but that I said, we did not see that much stratification as well as that much leaching difference. So the correlation holds basically this first figure is 0 to 4 inch depth, and again 0 to 6 inch depth. The correlation is very much similar. The strength of correlation also, like coefficient of correlation also very, very same. So we did not see any difference if we move from one depth to another depth. But if you think about the accuracy of the model, is still 0 to 6 inches more accurate than any other depth for the fertilization decision. So this is our updated. So based on all the data we have, we made a three-way regression model. The first is shown on the y-axis is a fertilizer K rate, and x-axis is a MELAC3 soil test potassium value, and on the z-axis you basically have a different level of yield. So this model helps you make a decision what yield level you want to be, like 90, 95%, and what is the soil test value and what would be the corresponding fertilizer rate. And based on this and also the individual yield response, we developed that recommendation table. So on the left side, we have the original recommendation, and this is our updated recommendations. So, and we use the sufficiency philosophy. Why did we use sufficiency philosophy? I will explain in a minute. But on this recommendation table, we have 5 different label. We changed the label little bit. We put optimum other than high and above optimum other than very high. We have this is our critical concentration, 91 to 130. And these are the probability level, the yield increase probability. On the very low and low side, we have 100% probability that producer can put fertilizer and be very confident to get a yield response. On the medium, we have like a kind of 50-50 chance. And there's the last column is our fertilizer recommendation. And you see that on the very low testing potassium testing soil, is we have 120, but our current recommendation only recommend 80 pound. That's the big change. We put 40 extra unit of fertilizer because of our current genetics. Like if you see in the top graph, is increasing all the way to 120 like a pounds per acre, and we have 10 sites. So we are very confident in increasing our fertilizer rate to maximizing yield. So let's go back to why we use a sufficiency philosophy rather than build and maintain philosophy. So this on the left side graph, that's again from the FAST, we published that. Most of the state using sufficiency philosophy, including Louisiana. Why? The question is the build and maintain, can you build up soil test potassium value? The answer is it depends, right? But the long-term study from Dr. Steve Coleman from Ohio, showing after 12 years, he put 0 rate, 1x removal rate, and 2 to 3x removal rate, and in 3 different soil, and he is not able to build any soil test potassium value. I'm sure Dr. Nathan Slayton has a 20 years worth of long-term trial. If I get his data, we may find out similar trend. And that's why, and again, our soil, this graph we already discussed, like we see even it is not a coastal plain soil, but in Mississippi Delta, still we see a very big amount of stratification, leasing, potassium leasing down to the soil profile. So that's how we get away from the build and maintain philosophy for potassium. So next is this is a very common question about making potassium fertilization decision. So which value of potassium do we need to consider? Either soil test potassium concentration or base saturation. This is very common question around this area in Louisiana, Mississippi, could be Arkansas, and also I heard from somebody from Midwest too. So this is the typical example. We have 2 different soil. One soil has a potassium concentration 189, is high, very high, but base saturation was 1.7. So just give you a reference, the base saturation of 2% would be ideal. So based on this soil test value, you do not need a fertilization for this soil. But based on the base saturation, you need to put some fertilizer. On the other soil, where the soil test potassium value was in the medium category or low category, 91, the base saturation was optimum. So if you think potassium concentration, you need fertilization. If you think base saturation, this soil does not need fertilization. So which one we need to think? So we tested from our research for both soil test potassium concentration and base saturation for soybean yield. The first graph that we already discussed, the MELAC3 soil test potassium concentration on the x-axis and soybean on the y-axis. And on the right side graph, the base saturation, potassium saturation on the x-axis. You see there is a clear difference about the strength of the correlation, also the accuracy of the correlation. You have the accuracy, both blue and green dot all over the place in the base saturation graph. But on the soil test potassium graph, all that responsive site on the left side of the critical concentration. And also the strength of the correlation or coefficient of the determination is 83 for that soil test potassium value, but only 55 for the base saturation. So the potassium concentration or salt test potassium concentration is very accurate for making fertilizer decision. But if you think about base saturation, you always need to, it always demands to put you some kind of fertilizer to satisfy the base saturation percentage, because this percentage is very influenced by the calcium and magnesium concentration. So let's move on the phosphorus, and I will go a little faster because it's very similar type of study we conducted. So the first graph represents that very low salt is phosphorus value, less than 10 ppm. And again, on the y-axis is the soybean relative yield, x-axis is the fertilizer P rate or phosphorus rate, pounds P2O per acre. So we have, again, 5 different fertilizer rate. And the major drawback of our study is we have only one trial under very low salt phosphorus concentration, but we got a significant yield increase. As the fertilizer rate increased, the soybean yield increased. The next soil, low soil phosphorus level 11 to 20, you see there is still a yield increment, and we have 20 trial until you hit 80 rate of phosphorus. The next is the medium salt phosphorus value 21 to 30. You see is almost a flat line. We have a hard time finding phosphorus response if the saltage value goes over 20 in this area. You see very small response here and there, but not very obvious. And on the optimum salt P level, more than 30 ppm, and again, it is flat line. So we again look at that all this zero control, unfertilized control rate when put in a correlate with a Melak-3 soil test phosphorus concentration, and it's not as clear as phosphorus. It's a little messy. And we expected that because the phosphorus correlation is not that strong like a potassium correlation. But still, majority of the responsive site on the left side of the critical concentration. So again, the critical concentration ranges from 22 to 28 ppm in this area. And the majority of the responsive site on the left side of the critical concentration. So this is the good sign of this model. And if you think about the critical concentration of our current current table on the medium, is ranges from 21 to 35, but we don't see that wide range of critical concentration. So we narrow the critical concentration a little bit in our updated model. So let's look at the different depth study. Again, this is the soil sampling depth and Melak-3 soil phosphorus concentration on the y-axis, and 0 to 4, 0 to 6, 0 to 8, and 0 to 12. And you see there is a really like it's declining as you move down to the soil profile. So it's a highly stratified phosphorus is on the top soils. No significant difference between 0 to 6 and 0 to 8, but still there is a numeric difference. But the correlation between different depth, like 0 to 6 versus 0 to 12, is still very strong. Like the coefficient of determination was around 90, 97 or 98. So very strong correlation again, but it's very stratified on the top soils. So we looked at that correlation for different soil depth. See, we can improve our critical concentration as well as the fertilizer recommendation. This is 0 to 4 on the left side and 0 to 6 on the right side that we already discussed. The correlation wasn't that strong. Well, it's similar kind of, but the accuracy is better on 0 to 6 than 0 to 4. And we look at the other two depth, 0 to 8 on the left side, like left bottom side, and 0 to 12 on the right bottom side. And again, the coefficient of determination, you can see 0 to 6 was the highest, but 0 to 4 was still good. And the reason behind that, you see the critical concentration also shifting towards the left side, like a lower zone as you move the soil testing depth. The reason behind that, again, the stratification. This is the one of the graph what figure is showing the phosphorus concentration is very high on the 0 to 6 inch, like 76 ppm. 6 to 12 is only 18 ppm. Then 12 to 18 is only 1 ppm. So it's highly stratified. That's why the critical concentration shifting as you're taking deeper soil samples. And overall, 0 to 6 inches is better than any other depth. So these are the, again, the multiple regression in the three-way interaction with the phosphorus fertilizer rate on the y-axis, male axis soil phosphorus concentration on the x-axis, and soybean relative yield. And these are the updated table that we developed that I mentioned earlier. The critical concentration of the medium level, we narrowed a little bit from the previous one, and 21 to 30 instead of 21 to 35. And we include a little higher rate on the very low soil, 90 pounds instead of 80 we had initial, like on the current recommendations. And again, on the very low to low zone, you have 80 to 100% probability to getting yield response. So producer still can have some confidence putting out fertilizer in the very low to low soil testing phosphorus value. Medium is only 20% chance or around 20% chance. So I'm not real confident putting out fertilizer in the medium zone and get a yield response. Okay, moving quickly, this would be my last slide. So now the question is, if the soil requires both phosphorus and potassium, which one you need to apply, or do you need to apply both or one? So this research, the interaction research, phosphorus and potassium, we conducted both for soybean and corn. Last year, unfortunately, we couldn't harvest our soybean due to chloride toxicity. So we harvested corn. I'm just presenting corn. So this is the site where the soil test phosphorus value was 12 ppm that requires 80 pounds P2O per acre fertilization. And soil test potassium was 75 ppm that requires 90 pounds K2O per acre. And that's the interaction study that we have. We have on the on the left side, we have the different rate of potassium, 0, 40, 80, 120, 160. And on the top side, we have 4 different rate of phosphorus, 0, 40, 80, 120. And if you see when there is a 0 rate of potassium, if you increase phosphorus rate, you are not really changing yield. With the changing of phosphorus rate, you are not changing corn yield. If you put little bit potassium, 40 unit, then you are changing yield with the phosphorus fertilization. If you put 80 unit, that almost the recommended rate, then you put 0, then you are really increasing yield with the increase of phosphorus fertility. So you get 80 rate of potassium and 80 rate of phosphorus, you get the maximum yield, like statistically maximum yield, 208 bushels yield. So this is very important, telling us if there is both nutrient deficient, you have to have both nutrient to get the maximum yield. But if you spend money for only one nutrient, the potassium would be that nutrient to spend money. But remember, only putting potassium, you cannot maximize yield, because you see all this yield, just putting potassium on the 0 P rate, you're not even getting the maximum yield. So making sure you got both nutrient, but if you spend one nutrient, potassium would be. So on the conclusion, so we have five conclusions basically to make. Our current soil test depth for 0 to 6 inch is still accurate. So producer can still trust 0 to 6 inch depth for both P and K recommendations for soybean in Louisiana. For critical concentration for soil test P vary with soil depth because due to the stratification. But soil test K, it does not vary because of the minimum stratification. Critical soil test P and K concentration do not vary with the soil texture. So regardless of your texture, you can use the same recommendation for silt-loam soil or sandy soil or clay soil for both P and K. And only one single critical concentration can be used for any texture for soybean production in Louisiana, and that critical concentration would be 20 to 30 ppm for phosphorus and 90 to 130 ppm for potassium. But if my soil test value falls close to the 20 ppm or 21, 22, I would make sure using fertilizer. And if it's close to the 30, then you can decide not to fertilization, but the soil test value for the next year would be little more down. And again, the same for the potassium. Close to 90, obviously need fertilization. Close to 130, you can think about avoiding fertilization for a year. And in the deficient P and K soils, both recommended P and K applications are really required for maximizing yield. However, potassium is somewhat more important than phosphorus in making yield. With that, thank you all, and thanks for this opportunity. And again, I would be happy to answer any question if you have.
Okay, so first off, I'd like to thank you, Rizal. That was a great presentation with a lot of information. And I think that's there's a lot of interest in this topic, and we do have time for some questions. So if anyone wants to go off mute, feel free to do so at this time and ask your question. Or if it's easier, put the question in the chat and we will jump on there. And I will give people, I have a couple of questions I wrote down, but I want to give people a chance to ask questions first.
Any thought to including some economics to your recommendation?
Yes, sir. I need you.
Okay.
Yes, sir. Yes, sir. We are in the process of publishing this data. So once it gets published as a recommendation, then yes, we'll move forward with the economics and may need your help down the road if you have no problem with that. But
sure.
I already talked to some of the economists over here in Louisiana. So
Okay.
since you already have experience, so
who's the economist that you're talking to?
Good question.
It's okay.
You know him. Not just coming in my mouth. I'll get to that point. Okay.
Sure, no problem. Good work.
Thank you.
So Michael, I appreciate that you asked that question, because I was going to ask something similar. And I just wonder, as you were listening to the presentation, I'm thinking about your talk from last month, or no, actually earlier this month. And I'm just wondering, did anything just jump out at you as something that would be a good area to dive into a little bit more from an economic perspective? What the end really interested me were the concept of the interaction between P and K, and how do we economically say what the right direction to go is. But love to hear you comment a little bit more if you want to.
Sure. I have not looked at interactions of P and K at this point. I made my recommendations on the basis of sufficient having non-yield limiting P available. And so I can only speak to the K part. It was interesting to see that you're differentiating your yield response curves by soil texture, and yeah, that's certainly something that would probably, because the shape of that approach to the yield maximum is so important.
Yeah, that's so we had that before, like based on the soil texture, different recommendations, but we don't see anymore this exist. That's why we tested so many different soils and come up with that. So there is no variation of recommendation for different soil texture. So
in terms of reaching yield max, I mean, this is your critical point there. But the shape on how to get there impacts the economics, and that does seem to be different. So there's room to talk there. I think it'd be interesting.
So you, Roselle, you kind of opened a, I'm gonna say you opened a can of worms, and I wanna bring it up. You commented on the let's say the debate between using K as a ppm pounds per acre value versus potassium base sat. And so
Yes, sir.
this is a great this is a great question that I think I get a lot, and I think a lot of the agronomists on the call probably get. So I would love for you to quickly reiterate your kind of position on which one we should use, and then I don't know if you have any thoughts about any of the other base sats and the usefulness, or another thing that we get a lot in the Midwest, I don't know how common it is in the South, is the ratio question. So like the ratio of one cation to another and things like that.
Great question. Great question. Okay. Yes, that's again, still the figure is up there. We tested all the ratios, best saturation percentage, to see we can have a better correlation with yield than the soil test potassium value. But we did not see the better correlation with the best saturation. The other thing is best saturation really depends on like how much calcium, magnesium, like all the other cation, but the two major one, calcium and magnesium, how much it is present. So you can think of a soil. If I go back to the previous slide, and you see the soil can have a low amount of calcium and potassium at the same time, but can have a better base saturation because the ratio can be better. See that the second soil, you have 91 potassium, the calcium only 1,000. That's why the base saturation come like an ideal zone, like more than 2%. But if you think about the other soils, well, the calcium is 4,000, almost 5,000 ppm. Still, the potassium has 190, but still the base saturation is less than 2%. So think about, that's why I'm saying the base saturation is kind of vague term. It depends on how much calcium and potassium present in the soil. And that base saturation varies. It doesn't dictate you whether you need a fertilization for maximum yield or not. But the soil test potassium does. That's why. And again, if you like to, let's say for this soil, if you increase the base saturation of 1.7 to 2%, that requires lots of potassium fertilizer, lots of potassium fertilizer, because of you have such a high amount of calcium to go over that 2%. So the base saturation always demands, that's why I concluded, base saturation always demands some kind of fertilization. But in true sense, you don't need to put fertilization based on base saturation. You just look at the soil test potassium value and make a decision.
I appreciate that response, and I think it makes a lot of sense. I'm just wondering, so first off, I saw Nathan, I see your comment in the chat. I guess I kind of did expect for it to be an issue in the South. I was just acknowledging that that's not where my expertise lies. But the other, so this specific data set has 61 sites, all of them in Louisiana, correct?
Yes, sir. Yes, sir.
Okay, so would you change your or do you feel like, how well do you feel like that would translate to a different setting outside of Louisiana? Your kind of your thoughts.
Okay, like Louisiana, Mississippi, and Arkansas is in the kind of same geographical location. It's just a invisible political border. So I'm very confident that that recommendation should work in any of these three states for the soybean production. If you looked at Arkansas recommendation, Dr. Nathan Slayton developed, is very similar recommendation. But the recommended rate of fertilizer is little different than our rate because the philosophy of the fertilization. Dr. Nathan Slayton used build and maintain philosophy, where the maximum rate of potassium is 160 pounds per acre for very low soil testing level. ours is 120. It's just a 40 unit different because of the maintained rate we are not using. So very similar. For Mississippi, they don't have a MELAC 3 data because their saltage value is a Lancaster. I can't really talk about that, but since again, by the Mississippi Delta is you are on the west side of the Mississippi or east side of the Mississippi, the production system wouldn't be that much different that I can tell.
That makes sense. I like your comment that they're just political boundaries, because I think that that really characterizes well what FIRST is trying to do. FRST, which we haven't talked a lot about. I know this presentation isn't technically part of FIRST, but it's this webinar series is kind of co-hosted or shared between Alta and FIRST. So I like that conversation comes up during the talk. So I'll open the floor if there's any other comments or questions. I will just say that the presentation is being recorded, and we will share out that presentation recording with everyone who registered, hopefully within the next day or two. But before we end it, I do want to leave the floor open in case anyone else has any questions or comments.
Hey, Corey, this is Nathan. Great job, Rassel. I want to put in a shameless plug for FIRST. Our decision support tool will go live next week on April 2nd or 3rd. So it'll be incorporated into our main FIRST webpage. So hopefully everybody will get on there and take a look at it and give us feedback. That's all I've got. Thanks.
And again, I'll say, Nathan, thanks for partnering with us over at Alta, and we will be sharing that link out as soon as it becomes available to everyone who's registered for webinars during these talks. So anyone else, feel free to go off mute. Otherwise, we'll wrap up.